Okay, so we've talked about how stable the benzene ring itself is, and so it resists many reactions. But carbons at the benzylic position are actually quite reactive. And so let's take a look at some of those reactions. Alright, so the first question you may have been asking yourself is, what the heck is the benzylic position? Well, the benzylic position is a carbon directly attached to the benzene ring. So this carbon and this carbon would be considered benzylic positions. So most of the reactions we're going to talk about is really just review of reactions that we've learned earlier. They just happen to have a benzylic position that we hadn't sort of identified before. And so when we look at this compound, it doesn't have any functional groups, right? You could argue that the benzene ring is a functional group, but it's not very reactive. And so when we have alkanes, or in this case an alkane attached to a benzene ring, the way to functionalize it is radical halogenation. And in Chapter 10, we learned about allylic bromination. Well, benzylic bromination works very much the same way. In the course of this reaction, we'll create a radical intermediate at the benzylic carbon. And not only is it stabilized because it's tertiary, but we can generate resonance structures with the benzene ring, and so that makes the radical here particularly stable, and so it makes us very likely to brominate at that benzylic position. So benzylic bromides also readily undergo substitution reactions. I don't think there's much new information here. We would have probably predicted these products even without having talked about benzene in this chapter. But I think it is important to note, because we have a tertiary alkyl halide here, we know it's going to proceed via an SN1 substitution as opposed to SN2. But even more than just being tertiary, we know that in SN1 process we're going to make a carbocation intermediate. And not only is this carbocation intermediate tertiary, but similar to being an allylic carbocation, this is a benzylic carbocation, and so we can draw a resonance structure where we move this double bond over, and then we can spread that double bond all throughout the benzene ring. So that makes this carbocation intermediate particularly stable, and so this reaction will readily undergo SN1 substitution when we have this tertiary benzylic bromide. In the case of this primary benzylic bromide, we would expect substitution to occur via an SN2 process. Also interestingly, normally when we have a primary alkyl halide, it's going to be primarily react via SN2, but then we'd also expect maybe a little bit of E2. But in this case, because the only possible carbon make a double bond with would be here, and because this carbon already has 4 bonds, that eliminates any chance of elimination, and so we're only going to get SN2 substitution with this strong base and strong nucleophile. All right, we also talked a lot about elimination reactions last semester, and these benzylic bromides readily undergo elimination as well. In the case of reacting it with this strong base and a tertiary benzylic bromide, we're going to get elimination. Or if I hit this alcohol with concentrated sulfuric acid, we'll get elimination through an E1 process. Okay, so I'd like to finish this video up with a new reaction that we haven't talked about before. Now, we've certainly talked about oxidation, but we haven't talked about oxidation of benzene rings. And we know that chromic acid, or sodium dichromate, is a powerful oxidizing agent, but it's not going to react with benzene or alkanes. However, if I have an alkyl group coming off a benzene ring, therefore creating a benzylic carbon, this compound can be oxidized. And so we actually chop off all of the alkyl group except for the benzylic carbon, and we install a carboxylic acid. Not only will this reaction occur with sodium dichromate or chromic acid, it'll also occur with another powerful oxidizing agent that we've talked about, potassium permanganate. And it does ultimately the same thing. So we need to do it in 2 steps with potassium permanganate. First with potassium permanganate and water, and then in the second step we'll finish it off with an acid to protonate the anion, but the end result is the same. We chop off the alkyl group and then we install a carboxylic acid at the benzylic position. Now, one important note about this oxidation reaction, we have to have a hydrogen at the benzylic position. In this case, there is no hydrogen at the benzylic position, and so the oxidation won't occur. So this is a kind of nice summary from the textbook, and I think this is particularly useful when we think about doing synthesis where we have a benzylic carbon. So when we have a benzene ring with an alkyl group coming off, or even multiple alkyl groups coming off, we need some way to functionalize that. And so we've learned two ways. If our end goal is a carboxylic acid, then we can oxidize it. The other thing, if we want to add a functional group that's not necessarily a carboxylic acid, and remember, converting to carboxylic acid is going to chop off the rest of the alkyl group. The other way to functionalize it would be through radical bromination using NBS and HNu. And so that's going to install a bromine at the benzylic position. And then we have lots of reactions available to us. We can do substitution to change the functional group, and then in particular, if we make it an alcohol, all the reactions that we learned with alcohols become available. If we use elimination to turn it into an alkene, then all the reactions that we learned with alkenes become available. So if you see a benzene ring with alkyl groups, you want to think either oxidation or radical bromination, and then a lot of the reactions that we've learned this semester are opened up to us.